Alright guys, welcome back to Underground Science, and in this video we'll be talking about a common example, just going over a disproportionation reaction. Alright, so a disproportionation reaction, as soon as you see this word, and we're talking about a reaction here in terms of chemistry, right? A disproportionation reaction is pretty much a reaction that involves an element that's getting reduced, that gets reduced and oxidized. That's reduced and oxidized in the same reaction. All right, so let's go and highlight that in the same, so the same reaction. All right, so that's when you know you're working with a disproportionation reaction. And a common example of a disproportionation reaction is when hydrogen peroxide, right, dissociates into water and oxygen. Okay, so let's go and look at that. So when hydrogen peroxide, oops, can't draw my H's properly today for some reason. Hydrogen peroxide, when hydrogen peroxide disassociates into water and oxygen, we see a disproportionation reaction. All right, let's add more space here because we'll have to balance this out. So water and oxygen. You know what? Let's make a whole space as more space as a whole because we drew this arrow too big. All right. So again, this dissociates into water and oxygen. All right, but first of all, before we continue talking about it, we have to balance this. Remember the law of conservation of matter. We have to balance the number of atoms on one side to the other side because the number of atoms has to be equal. So let's start off by balancing oxygen. I mean, that's the only thing we have to balance. All right, so let's go and look at this. So let's see. So if we look at this, we have 2 oxygen molecules here on the reactant side, and we have 3 oxygen molecules here on the product side. And we have 2 hydrogen atoms on the reactant side, and we have 2 hydrogen atoms on the product side. So what we really have to do is, all we have to do is just add a 2 over here, right? If we just added a 2 over here, what would happen is this. Now we have 4 hydrogen atoms here on this side, the product side, and we would have 4 oxygen atoms, right? So we would have, let's go and write that down. We would have 4 hydrogen atoms on the product side, and we had 4 oxygen atoms on the product side also. So instead of making this look like a 40, let me just go and write like atoms here. So we know we're talking about 4 oxygen atoms and 4 hydrogen atoms. Okay, but here we only have 2 of each. So all we have to do here is also add a 2. Okay, and we're balanced. So now we're going to have 4 hydrogen atoms on this side, right? Oops, I erased that by accident. Sorry about that. We're going to have 4 hydrogen atoms on this side, 4 oxygen atoms on this side. Then we're going to have 4 hydrogen atoms on this side, and we're going to have 2 plus 2 oxygen atoms on this side, making 4 oxygen atoms also. So we're balanced. Okay, so now let's see how this is a disproportionation reaction. Let's go and write this down right here, give us more room. So we have our 2 hydrogen peroxide molecules. Then we're going to have it dissociate into our 2 water molecules and our oxygen, a diatomic oxygen. Okay, so now so remember we said what? We said a disproportionation reaction is when an element is reduced and oxidized in the same reaction. So this is just one reaction, so let's see which element that is. Okay, so usually, right, when we see a disproportionation reaction, usually, actually in any reaction, in most cases, oxygen is, you could, when you assign the oxidation numbers, which we'll try to look at more examples in another video, but the oxidation number for oxygen is usually going to be -2. Okay, so and why is that? Is because oxygen is in group 6A in the periodic table, okay? So it can gain 2 electrons and become neutral. All right, so I got a picture here. So see how oxygen is in group 6A of the periodic table, or you can say group 16, either one. And usually oxygen, you're going to have an oxidation number of -2, right? So knowing that, we can see that in this reaction, right, in our hydrogen peroxide reaction, here we see that the total charge, and always you have to remember that the total net charge in our compound alone has to equal 0. So if we give a -2 charge to oxygen here, we have 2 oxygens. Okay, and if we're disregarding the coefficient 2, we have 2 oxygens here for hydrogen peroxide. So what that's going to lead to is a times 2, which is going to be -4 total oxidation number for both of our oxygens. But then hydrogen, the problem with this is that in this reaction, hydrogen is going to have an oxidation number of +1. Okay, so because it's right there, it can easily gain an electron and become neutral. So that's why oxygen is going to have an oxidation number of +1. Well, as you can see, right, it doesn't match because +1 times 2, because we have 2 hydrogens, is equal to +2. Remember, because we don't have any net charge on hydrogen peroxide, our total oxidation numbers, if we add them together, has to equal 0. Well, +2 minus 4 equals -2. It doesn't equal 0. So in this case, we have to be careful, and we have to know that in this case, our oxygen is going to have an oxidation number of -1. Okay, so usually you can identify it like that. Usually you can just go ahead and say that in most cases, hydrogen will have a +1 oxidation state, so you can go and work your way after finding out hydrogen's oxidation state, right? You have to work around, and we'll see more examples of that in a future video. So in reality, what we just said is oxygen is going to have a -1 oxidation number, and hydrogen is going to have a +1 oxidation number. This will lead to -1 times 2, because we have 2 oxygens. We'll have -2 charge here, and +1 times 2. We'll have a +2 charge here, and then +2 minus 2, right, is equal to 0. Right, and we have to make sure that it is neutral because we don't see any net charge here in hydrogen peroxide. All right, so that's done. So what do we say here? So let's go and write it down. So oxygen has a -1 oxidation number, and hydrogen has a +1 oxidation number. Let's look at the product side now. Here, oxygen will have to have a -2 oxidation number now. Okay, why is that? Because we only have 1 oxygen here, but we still have 2 hydrogens. So if we still keep the same for hydrogen, a +1 oxidation number, +1 times 2, all right, +1 times 2, because we have 2 hydrogens, is going to yield a +2 total charge for both our hydrogens. Again, we're excluding the coefficient for now. Okay, and then we only have 1 oxygen, so we're only going to have a -2 charge. So if we subtract our +2 from our -2, it's going to yield a neutral oxidation number of 0 as a whole, right? We don't see any net charge on H2O because it's water. So we need a total sum of 0, and we got that from +2 -2. Okay, so this time we have an oxidation number of -2 for oxygen because we only have 1 oxygen. Okay, and you have to see that if there's any net charge on here, which we don't see, so we know that in total, after we assign our oxidation numbers and we add it together, this time counting the coefficients inside, right, not the outside coefficient, then we should see that our net charge should equal 0, okay, that we see here. And even though you do include the outside coefficient number, you're still going to get 0, right, because we have +1 oxidation number of hydrogen times 2, which is 2 plus, again times 2 because of the coefficient, which would be 4 plus, and then we have a -2 for 1 oxygen times 2, which is -4, so 4 minus 4 is 0. So you can still count this in, but I'm not counting it in just to make it easier so we have lower numbers. Okay, and then here, another rule is that if you see an element that's just by itself an elemental form, which is what diatomic oxygen is, it's an elemental form, the oxidation number of any elemental form element will always be 0. So this has no oxidation state, right? It has a 0 oxidation state. So no net oxidation charge on it. Okay, so now we have to look at what's being oxidized and what's being reduced. This is a disproportionation reaction, so we're looking for one element that's being oxidized and reduced in this same reaction. So if we look at this, we have oxygen as a -1 charge here. Then here we have an oxygen with a -2 charge. Right away that tells us that oxygen, and just from this to water, got what? Reduced, right? It gained an electron because it increased in negative charge. But at the same time, if we trace this pathway, right, all the way here, what do we see? Oxygen went from a -1 charge to a 0 charge, which means oxygen got oxidized in this particular pathway in green. Okay, so this is what a disproportionation reaction is. Okay, one element getting oxidized and reduced in the same exact reaction. Okay, so oxygen here went from -1 oxidation number to a -2 oxidation number, so it got reduced. But at the same time, it went from a -1 oxidation number to a 0 oxidation number. So here it got oxidized because it became more positive, right? It went from -1 to 0 means it lost an electron and became more positive. Okay, so the reason why this hydrogen peroxide dissociating to water and oxygen is a disproportionation reaction because oxygen got reduced, and oxygen got oxidized in the same reaction. All right. So if we were to go ahead and write out the specific, right, and not the whole compound as a whole, but if we just separated the oxygen out, we would see that we had, let's go and rewrite it here, but just the oxygens, right, nothing else. We would see we started off with an O2, part of the hydrogen peroxide. I'm not writing the hydrogen or the other two H molecules or the coefficient of 2 because we're just focusing on the oxygen. All right, so we start off with an oxidation number of -1. Let's go and write that in a red color so we can differentiate it. All right, and we went to, so remember, this is still part of hydrogen peroxide. I'm just not showing it because I'm trying to show you guys and learn how or why this is a disproportionation reaction, right? Because of oxygen. Okay, and then we went to H2O. The oxygen H2O has a -2 oxidation number. So this is the oxygen for H2O, and we have a -2 oxidation number here. And let's go and rewrite it again and look at the other oxygen, all right? So in the diatomic. So this is, again, the two oxygen part of hydrogen peroxide, right? And then we went, now look, if we go and look at the diatomic oxygen right here in specific, let's focus on here, and we have a 0 oxidation number here. So in our diatomic oxygen, so here like this, we're going to have a 0 oxidation number here. All right, so I'm just going to write just to differentiate these two so we don't get confused, is that remember that this is still, we still have hydrogen peroxide here. We still have our other two hydrogens. I'm just not showing it because I'm focusing on the oxygens. All right, so remember, this is still part of the hydrogen peroxide. All right, so now we can see here clearly that oxygen went from a -1 oxidation number to a -2 oxidation number. So because of our oxidation number, we see that if we go from a -1 to a -2, you're getting more negative. So we're getting reduced here. Oxygen is getting reduced, all right? We're getting added a negative charge, right? That's what reduced means. We're gaining an electron. Okay, and over here we see in hydrogen peroxide again, it goes from a -1 charge except to a diatomic oxygen. Remember, any element in elemental form in a reaction will have an oxidation number of 0. And so -1 to 0 is going to be an oxidation reaction because if we get oxidized, we lose an electron. And if you go from -1 to 0, you're becoming more positive. So if we lose an electron or lose a negative charge, we become more positive. So here, oxygen is getting oxidized, all right, from hydrogen peroxide to diatomic oxygen. Okay, so this defines our disproportionation reaction. The same element, oxygen, is getting oxidized and it's getting reduced in the same reaction. And that's what a disproportionation reaction was, right? That we defined right here. An element that gets reduced and oxidized in the same reaction. And for this video, we looked at hydrogen peroxide, and the winner is oxygen, all right? That's the element that was getting reduced and oxidized in the same reaction. All right, so that was our video for disproportionation reaction. Hopefully that made sense to you guys. In my future videos, I'll talk about more cool topics about biochem, and chem and physics. And so I really hope to see you guys there. Don't forget to hit that notification bell and like and subscribe, and see you guys later, and stay safe.